Right, we'll do a few quantitative electrolysis problems. We'll do these step by step. Oftentimes there are 4-step problems. We might be able to boil this down to just a 1-step solution. We'll see. Alright, so in the picture you see the plating of copper onto a cathode, which might be a tin spoon or a key or a piece of jewelry or something like that. We want nice shiny copper on the surface of that. The variables in these problems will be the electrodes themselves, in this case copper, the ions, copper 2+, cations are used. Most importantly, the moles of electrons gained at the cathode per mole of reaction. So here, for the half reaction as written, per mole of copper formed, or per mole of reaction, there's 2 moles of electrons gained by the copper 2 cations. The external power supply or battery will provide a particular current and amount of charge per second. We measure this in amps or amperes, and 1 ampere is quite a lot of charge. It's 1 coulomb of charge per second. And a coulomb of charge is provided by 6.25 times 10 to the 18th electrons. Another variable, since you have coulombs per second, we'd like to know how many seconds you're going to supply the current from the external battery. Sometimes, though not as commonly, you'll be given the power of the power supply. The physics formula for power is voltage times current, so you'll be given, let's say, a 12-volt battery, and that's supplying 3 amps of current, so 12 joules per coulomb times 3 coulombs per second would be 36 watts. So you could just take the power rating and eventually convert that to a current rating, which you're going to need in the electrolysis analysis. And finally, there's the efficiency of the battery. Not all of the charge from the current, or not all of the current, is used in the actual electrolytic process. There might be side reactions, there might be, I don't know, some kind of wasteful eddy current, something's going on that's going to lower the efficiency of the battery. And these can be tricky questions or very direct. We'll get to that. So let's see how all of these various variables can be combined to come up with some useful information. We'll try to put this in an all-in-one formula and then do the problem either in steps or just all at once. So we have some generic substance D and D cations with an N+ charge will have to gain N moles of electrons to form 1 mole of reduced D per mole of reaction. So let's look at the current, the rate of charge flow through the cell or circuit. That's going to be the amount of charge per time. Q is the symbol for charge per T, or delta Q over delta T, either way. And in terms of the reaction itself, there are going to be a certain number of moles of electrons gained at some given moment. We want the moles of electrons to be converted to charge, so we use the Faraday. That's the amount of charge per mole of electrons. So that's basically what Q is, moles of electrons gained times charge per mole. That'll cancel the moles of electrons, and we divide by time. So the moles of electrons gained times the Faraday divided by time is going to be equal to the current. And that's just rearranged to get moles of electrons gained after a certain amount of time with a given amount of current. We rearrange this equation here and isolate moles of electrons gained, multiply both sides by T, divide both sides by F, and it's simply IT over F. Current times time, coulombs per second times second, divided by Faraday, which is coulombs of charge per mole of electrons, and everything cancels except the 1 over inverse mole of electrons, which gives you moles of electrons. Now we're interested in how many moles of D will form using that current for however long an amount of time. So we have tautology here, a necessary equality. however many moles of D formed, that's going to be the moles of D per n moles of electrons gained, and at a given moment in time we'll have a certain number of moles of electrons gained. So substituting for moles of electrons gained as IT over F, that's over here, which we had previously solved for just by looking at units and current considerations, you can get your overall number of moles of D, let's say plated on a spoon or something like that, by just multiplying 1 mole of D per n moles of electrons gained, or basically the inverse moles of the electrons gained times IT over F. And this is a key one-step equation. You'll have 4 possible things that can vary: the current, the time, the moles of electrons gained per mole of substance formed, doesn't have to be D, and X will be, I'll use for moles of D, so I don't have 2 n's in the problem. 3 of these 4 variables must be given, and this way you'll just have 1 unknown. So without the long formal names, this boils down to just moles of D is IT over moles of electrons per mole of D formed times F, the Faraday. F is not a variable, it's a constant. It's 96,500 coulombs of charge per mole of electrons always. One more possible formula, which just relates moles to grams. We define moles of D formed as the grams of D formed divided by the molar mass of D, or the gram formula mass of D. And so substituting these 2 variables for the one variable, x moles of D, we have a slightly longer formula for which we could solve for grams of D formed or plated on wherever at the cathode of the electrolytic cell. And the only other multiplier that's going in there is the molar mass of D. So it's the same formula as the mole formula, and of course moles times the molar mass is grams. You knew that anyway, so you don't really need both formulas. Here you have 5 variables, 4 of which must be given, and it comes down to just that simple formula. There are a couple of permutations that can be asked for. Whoever's writing the question may want to know what current is required to produce a certain quantity of moles of D. So just rearranging the moles formula, isolating I, the current, we rearrange the formula and you get I equals moles of D times moles of electrons gained per mole of D formed times the Faraday divided by time. Again, 3 of these 4 variables will be given. The Faraday is not a variable. Do the units check out? Well, current is coulombs per second, or amperes. X sub D is moles of D. N sub electron is moles of electrons per moles of D formed. Faraday is in coulombs per mole of electron, and time is in seconds. So yes, everything cancels except for coulombs per second. So that equation works out fine. Another variable or rearrangement they may have you make is how long would it take to plate a certain number of grams of copper or whatever given a certain amount of current. So here they have to get you to the moles of the substance plated. They have to give you a way of getting the balanced net half reaction, so you know the moles of electrons per mole of D formed, the Faraday, and the current. And again, three of those 4 will be given, and you solve for time in seconds. And you see the units work out beautifully. So here's a typical question involving, well, we'll see what the variables are. Determine the mass, so they want the grams of copper metal that can be deposited on the cathode via electrolysis of an aqueous copper 2 sulfate solution, given that the current is 3 amps, so that's the I, is supplied to the cell for 2 hours. So That's the time, although we'll have to convert that to seconds, and there are 3,600 seconds per hour. So we have the reduction at the cathode, copper 2 plus, cations turning into copper. So that's going to require 2 moles of electrons per mole of copper formed. So that's a key. N sub E is going to be 2. 2 moles electrons per 1 mole copper formed via reduction at the cathode. We need to determine the moles of electrons gained in 2 hours. So the amount of charge is current times time. We're given a current of 3 coulombs per second. It's 3,600 seconds per hour. That's a constant you should memorize and always know. And that's for 2 hours. So you see the hours cancel the seconds, cancel, one from the time, one from the current, and that gives you the total amount of charge. And then we'd like, most importantly, to use the half reaction equation as written, the moles of electrons delivered in that 2 hours time. So that's just going to be the charge delivered, which we already have, because coulombs is the only unit remaining, and then times the Faraday. So we multiply IT times the Faraday, 1 mole of electrons per, I'll use the 5 sig fig Faraday, 96,485 coulombs, and that gives us 0.224 moles of electrons delivered by that current in that amount of time. Put that in the balanced equation, half reaction, and 2 moles of electrons will get us 1 mole of copper, so 0.224 moles of electrons will get us just 0.112. It's a 2-to-1 ratio, moles of copper. So we have to convert that to grams. 0.112 moles of copper plated onto the cathode in the 2 hours with that 3 amp current. Copper is 63.55 grams per mole, so it would be 7.12 grams of copper plated. Now, would the handy-dandy mass formula have worked in one step over here? I don't like doing things in one step because you kind of lose the logic, the step-by-step meaning, but we kind of derive that to get to this formula, so let's just see whether it works. The one-step equation for grams of the substance, copper, IT over the moles of electrons per mole of reaction times the Faraday, and all times the gram formula mass. So we have 1 mole of copper per 2 moles of electrons. That's the N part. I, the current, T, the time in seconds, 7,200 seconds. That's 2 hours worth of time. Faraday in the denominator, and then the gram formula mass. Wow, you get 7.12 grams of copper, just as we did the logical 3 or 4 step way. So that worked out quite well. Here's an efficiency component of the question. If this electrolytic cell process were 85% efficient, that means 15% of the current was wasted, was not going towards plating the copper. The mass of copper that would have been plated, given an 85% efficiency, is 85% of the mass of copper that's plated at 100% efficiency, of course. So that's the direct, easy efficiency question. 85% of 7.12 grams of copper is 6.05 grams of copper plated. And again, that's because 15% of the current was wasted one way or the other. And now for the tricky way that the efficiency part of the question can be asked, and this will trick you every time, unless you're very careful, so follow the advice. I could easily get it wrong myself. So, the advice is, number 1, get a qualitative answer. Qualitative. Will it take, well, let's read the question. If the electrolytic cell battery were 85% efficient, just as it was in part B, how much time would have been required to deposit 7.12 grams of copper? Okay, so what is everybody going to do? They'll take 85%, 85/100ths of the 2 hours time, or 7,200 seconds it took to plate the 7.12 grams, and you'll get a number less than 7,200. Well, that's completely dead wrong, illogical, and just flat out dumb. And the reason is, the simple reason is, when the battery was working at 100% efficiency, no wasted current, 3 coulombs per second were going towards plating the copper, it took 2 hours to plate 7.12 grams. So with a less efficient, wasteful battery, go ahead and figure that it's 1% efficient. It's certainly going to take a lot longer than 2 hours to plate the 7.12 grams. So at the very least, if you get an answer that's qualitatively wrong, you at least know you're wrong. So write that out somehow. Now to get the correct answer, and here's one way. I'm sure there are many ways, because some people like proportions, other people like ratios, etc., etc. Whatever you do, you should like logic, a logical way. So here is a logical way. We know with the 85% efficient battery, after 2 hours, merely 6.05 grams would have been plated in 2 hours. So it's going to take more than 2 hours to get up to that 7.12 grams. In fact, 2 hours, or 7,200 seconds, we could just say this in an English sentence, 7,200 seconds, 2 hours, is 85% of the required time to plate out the entire 7.12 grams. So is an equal sign. 85%, you can use 0.85 or 85/100ths, whatever you want to do. 85/100ths of the time required to plate out the entire amount. It's not 100% of the time required. We're at 7,200 seconds, and we're 85% there. How do we know we're 85% there? Because they're telling you it's 85% efficiency. How do you know we're 85% there? Because 6.05 grams is 85% of 7.12 grams of copper. So we just have to solve this equation for t. So the time required at this 85% efficiency, multiply both sides by 100 over 85, and you get 8,470 seconds, which is a little more than 2 1/3 hours, a little more than 2 hours 20 minutes. So qualitatively this is right, and it sounds right. It's going to take longer at this 85% efficiency rating to get the 7.12 grams of copper plated.